Okay, so our last video we sort of ended um, with a frequency distribution table. So we've done two of those now, one for our happiness scores and one for our grouped data, the exam scores. What I want to do for this video is talk a little bit about graphic representation of a frequency distribution table. Okay, and what we're going to create is a frequency, something called a frequency histogram. Okay, some people will call it a frequency histograph. Some people call it a bar graph. It's technically not a bar graph, but we can get into that later. What we're going to do is sort of show a pictorial representation of our data set. Okay, and the way we do this, let's make our y-axis here and our x-axis this way. Okay, and let's take a look at our happiness data set. Okay, that should be right in your notes. And remember, we have our x column, which includes all of our possible scores, right? 10, 9, 8, 7, 6, 5, 4, 3. And we're going to look at our frequency column. And if I look through there, I'm going to look at the most frequent score, which is also called what? The mean, okay? Most frequent score was 8, and that occurred 16 times. That is 16 people reported a happiness score of 8. So I want to make sure my y-axis here is going to be my frequency, okay? So I want to make sure I have at least 16 here, and you'll see how this unfolds as we go along. So let me do it this way. Let me do 5, 10, 15, and then 16 would be here. Okay, and of course 5 would be 1, 2, 3, 4, 5, and then 6, 7, 8, 9, 10, and so on and so forth. Okay. Then on the x-axis, we're going to have our values from lowest to highest, right? Just like we read from left to right. So we have 3, 4, 5, 6, 7, 8, 9, and then let's go out to 10. Okay, so those are our scores. Okay, now here's how we're going to do this. We look to see how many people, that is, what is the frequency of the people that reported a 3. And when we look at our frequency distribution table, we see that 2 people reported a score of 3, and I'm going to make this 2 boxes here, and have them come down like this, right? So 2 people reported a score of 3, and then I'm going to look and I see 2 people reported a score of 4. Okay, and then 4 people reported a score of 5. Trying to be neat here, but it's not perfect. I'm going to let a computer do this afterwards, but we can do this by hand for now. What's interesting here is I want you to take note. See where this line, this vertical line comes down? Guess where that comes down? Technically, it comes down at 3.5, which is also what? The upper real limit for 3. Okay? And it's the lower real limit for 4. In fact, that's a shared boundary. Okay? Sometimes people say, well, what would happen if somebody got a 3.5? Where would they go? Well, if somebody had a 3.5, then our whole graph would change. We would have a graph with decimals on it. Okay? This is just, we know that it underlies the continuous variable, but we have no way of measuring that. Likewise, this line technically comes down at the upper real limit for 4, the lower real limit for 5, and so on and so forth. Okay, but we don't need to put those in there, but it's just sort of a pictorial representation of our upper and lower real limits. You know, they're really there, but we just have no way of measuring that with the instrument that we had for happiness. So let's continue, okay? 13 people reported a happiness score of 6. So we're going to be something up around here. And by the way, I guess I could put in these lines, but it starts to get a little bit cumbersome, right? I'm showing you these lines for a reason. I typically don't do anything for no reason, okay? Oftentimes you won't see these lines, so you'll see a frequency histogram that looks like this. Okay, that's what it'll look like, and those lines will be gone. But I want you to be sure that you understand that every person gets one block that's the same size, okay? And we're just going to stack these. So the fact that this bar here is higher than this means that there's more people under here, okay? This is not a very challenging concept to understand, but once we get into some of the other graphs, and this is, you may have already sort of noticed this happening in this class. We're going to start with some simple concepts, and then we're going to grow them into more complex concepts that we can deal with, okay? But typically you won't see these, okay? You'll see a frequency histogram that looks like this. That's okay. So for 7, how many people said they had happiness of 7? Well, that was 15. So we're going to go up like this, right? And then for 8, it was 16. And then for 9, it was 7. And then for 10, we're back down to 2. Okay. So there we have it. This is our frequency histogram for our happiness scores. And you can sort of see, of course, one of the things that you can see from this frequency histogram is the mode, because the mode is the most frequent score. So it's the place where we see the highest point in the graph, which is right here, right? And we look down and we say, okay, the mode is 8. Okay? It's a pictorial representation. It also sort of shows you the distribution. There's lots of people at 8. There's quite a few people at 7. As we move away, as we get to the lower numbers, there's not as many at the higher as well. And we'll talk about some general shapes of these curves a little bit later in the video. But this is called a frequency histogram. Okay? Now, I'm going to show you, and this is very common, and it's typical for the frequency to be on the y-axis and for the numbers to be on the x-axis. I have seen journal articles where this is sort of switched, where the frequency is here and the numbers are here. I don't like that style as much, and it's certainly not as common as what you see here. I'm also going to talk about something else that I don't particularly like, but that they'll talk about in the book, and we will use it illustratively in a couple minutes, and that is something called a frequency polygon. Okay, and what we're going to do to make a frequency polygon is we'll put a point here, we'll put a dot midway in this interval of 1, okay, like this, And then what we're going to do is connect the dots, okay? And we'll start at the 0.4, sorry about that. We'll start at the 0 point here on the x-axis, and we'll connect the dots here like this, okay? We'll connect the dots. Just connect these, and it creates like a little mountain, right? In this case, it's a polygon, right? We're creating this polygon. And if you did this, you know, all of these underlying and overlying, I suppose, too, this would all be erased. Again, some people use polygons. I don't particularly like them. I like the straight up frequency histogram a little bit better. But this is what a frequency polygon is, and I'll be talking about that in a few minutes in terms of talking about general shapes of curves. Okay, so this is in a way a pictorial representation of some of our frequency distribution table. That is, we have our x values here and our frequencies. And by the way, when you do a graph, I mean, I would prefer that you label your graph. Just because you have numbers here doesn't mean that you've labeled this. So this would be, maybe I'll label this as self-reported happiness. Okay? And this is the number of people that are at each of these points. Okay? So let's do a frequency histogram for our fictional exam scores, right? The other data set that we made a table of. Erase this all, and I'm going to set it up in the same way generally. Okay, and that is, I'll have my frequency here. All right, and I'll have this would be what, exam scores in terms of percentage. And we grouped the data in this case. We started in the 40s, right? 40 to 49, 50 to 59, 60 to 69, 70 to 79, 80 to 89, and then 90 to 99. Okay. Now, some people, I know, you know, when people learn some of these graphing procedures in high school, for example, your teacher might have said, hey, you should start at 0. There's a reason why you might want to consider starting at 0. You don't want your graph to be distorted. In this case, though, it's kind of silly to start at 0. We had nobody that got in the single digits, nobody that got in the teens, 20s, 30s. If I included that, they would all be at the baseline anyway at 0. So I'm not going to start this at 0. It's kind of silly. Also, sometimes you have data, the data set, all of the numbers are in like the 300s. And why would you have a graph that goes all the way down with nothing here with 0? Okay. And then sometimes people learn in high school as well that if you don't start at 0, make sure you do one of these little things here that shows that that's, discontinuous from the 0 point. And I always find that quite silly because what I always say is, as soon as I saw that 40, I knew that you weren't starting at 0. So putting that little, hash line in there doesn't really give me any more information. So, sometimes you are taught some things that you have to unlearn, perhaps. Okay, this graph would look silly if we started at 0. That's just the way it is. for our frequencies now, the highest frequency we had, of course, our data set was only 17 people, right? The highest frequency that we had was 6, so I only need to go up to 6. It's going to make it a little bit easier for this graph. 1, 2, 3, 4, 5, and 6. And I can actually put all the numbers in here. I mean, why wouldn't I? It's manageable in this case. And now we can start putting in our boxes for this distribution. So one person scored in the 40s. Guess where that's coming down? Guess where that vertical line's coming down? At 49.5, okay? Which is a lower real limit for 50. It's an upper real limit for 49. Everybody with me? One person scored in the 50s, okay? 2 people scored in the 60s. Now, I'm just going to make this into 2 boxes just so that you can see. I mean, the reason that this bar is higher is because there's 2 boxes there, right? But all of the units of this graph are these boxes. How many people in the 70s? 6 people in the 70s, okay? And that was our modal interval. Oops, wow. Okay, do that. 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. In the 80s, 4 people in the 80s. Okay. And then 3 people in the 90s. All right. So there we have our graphic representation of our data set in terms of this frequency histogram. Get this information from our frequency distribution table. Kind of interesting as a historical factoid, if you look at early journal articles, let's say from the 1950s, 60s, 70s, 80s even, you'll see a lot of frequency distribution tables, because when we have a table like that, it can be typeset. It's much easier to typeset. As the technology improved for doing graphs in journals, nowadays, let's say from 2000 onward, you're much more likely to see a graph than you are a table. Okay, and for a frequency histogram, again, you're much more likely to see something that looks more like this, without the lines. You're much more likely to see that. But I do want you to remember that the height of these bars are dictated by how many boxes are stacked up, okay, how many people are there, what the frequency is, okay? And again, we could do a frequency polygon from here if we just put our points halfway through this interval. I mean, now the interval's 10, but it's just going to be halfway through there. We'll connect the dots. And again, I'm not going to go through and try to erase those bars, but a frequency polygon typically just includes those lines and not the bars. Okay, that's how you do a frequency histogram. Once again, it kind of tells people we can see what the modal interval was here. It's the highest point in the graph is the mode, and we see that there are lots of people in this, and then as we move away from that, we see fewer and fewer people. Okay, so that's frequency histogram. Now, sometimes, well, let me go back here. If we look at our happiness scores, we had 3, 4, 5, 6, 7, 8, 9, 10. If I were in, you can look at the graph that we just made. If I were going to present these data, data is a plural word, okay? So, I mean, some professors have little pet peeves about that. I don't really care, but technically data is a plural word, so you should say these data, not this data, okay? These data. The singular is datum, D-A-T-U-M. Anyway, if I was presenting this at a research conference, I might, in this case, consider also reporting 2 and 1 even though they're at 0, right? Even though they're at 0, I mean, I don't know what the rest of this is. I might actually consider reporting these. Now, this seems like I'm contradicting myself from what I just talked about with our test scores, okay? The test scores, I certainly wouldn't start at 0. It's too much stuff, and I don't really care about that. In this case, by including 1 and 2, I can actually show whoever wants to look at this data, whoever the consumer is, I can show people every possible response because we let people, remember it's a Likert scale from 1 to 10. And so it might be worth it for me to say, well, of all the possible responses, nobody chose these 2, and then we have the rest of our frequencies. Listen, you guys, and I've talked about this in the last video. Oftentimes there are no fast rules. That is, you don't have to do anything. What you want to do is what makes most sense for your goals. Okay? What do you want to accomplish? How do you want to describe the data set, right? Remember when we were talking about, if somebody got 100 on the exam, I would just tack that onto the top, even though it sort of violates one of those guidelines. I'm not worried about it. I wouldn't be obsessed about starting my graph with 0 or starting it with the lowest possible number. But in this case, it only includes 2 numbers, and then I can show people all of the possible, the potential responses. So these are decisions that you make as a professional rather than following some rules that are hard and fast. Okay, so I just want to show that. We didn't talk about something called nominal data, and that is when you categorize information rather than quantifying them. But sometimes, let's say you're running an ice cream stand, right? And you sell chocolate, vanilla, and strawberry ice cream. Wow, really exciting, right? And you keep track of people's, how many of each of the flavors that you sell. Well, I mean, those data might be useful, especially if you're ordering more ice cream, right? We can look at frequency. How many people bought chocolate, how many people bought vanilla, how many people bought strawberry. So down here you would have your flavors. Okay, so you could have chocolate, vanilla, and strawberry. Or what? Well, you could have vanilla, strawberry, or chocolate. That is, these are just categories. They don't occupy spaces on some continuum. And who says chocolate should go first? Maybe vanilla should go first. Maybe strawberry should go first. Okay? But in this case, now you would keep track of, how many people bought each. And you might see that this many people bought vanilla. This many people bought strawberry. This many people bought chocolate. Okay. Chocolate ends up being our modal flavor. That is the one that is the most frequently chosen. But notice the difference here, and by the way, technically, people call this a bar graph. The other one was called a frequency histogram, right? A bar graph is when you're graphing categorical data. Notice that these bars here do not touch because they're not on a continuum. And I've seen people do an Excel spreadsheet graph, and they do a graph like this, and these are touching, and it's kind of weird because it implies that there's some kind of a continuum when there's not, okay? Also notice that, you know, if we put chocolate first, this highest bar would be here, and there's no a priori reason why you would have, why these are ordered, so you can put them in any way that you want. So those are sort of the two technical distinctions between a bar graph and something called a frequency histogram. Okay, these are categories. They don't belong on some kind of numerical continuum. Okay, everybody good? Okay. So let's look at now a sort of a conceptual frequency distribution histogram, and I'm not going to put any actual numbers on, but here's what we're going to do. We're going to have a number line, okay? And since this is a number line, of course, it consists of different x values that lie along a continuum, okay? And I don't care if it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever, or if it's 2057, 2058, 2059, 2060, 2000, just doesn't matter. That's what I mean by sort of this generic number line. When we do a frequency histogram, along the y-axis is frequency, okay? But in this case, I'm going to not draw the axis, and this it'll become clear in a minute why. Oftentimes, it is an implied axis rather than an actual axis. But I'm going to start to plot some numbers here, and let's do this. Let's say that this is the value that we see most often, okay? And when I draw that bar, I want you to understand that it's that high because there's that many people, the frequency, right? It's a little bit tedious, but I'm doing it for a reason, okay? You see something like that. And let's go now one step up on our number line, and we'll do one fewer for the frequency. Again, oftentimes when we make these, and most of the time, when we make these graphs, you don't see these horizontal lines, but I like to put them in there. There's a reason why I'm putting them in there, because I want people to understand that the height of the bar is related to the frequency that we see at a given score, okay? And we'll go down this way. I'm not going to be too careful here. And then we'll go down one in terms of frequency as we move up in the value of x. Likewise, we'll do that here. Okay. And we'll keep going with this pattern. Everybody with me? We're going to keep going with this pattern. We'll keep going with this pattern. Keep going, keep going, keep going, keep going. And I'm going to ask you to think about this because I'm going to run out of board space here. But I'm going to keep doing this kind of a strategy. And if anybody's really good at math, it's not exactly this pattern all the way through. But I'm going to finally get down to a point here, somewhere far out here, where I only have one. And then I have two, and then I have three. Okay? And out here, actually, it's going to be symmetrical. We're going to see the same thing that, this graph is going to go down. Okay? And we'll fill in all the rest. Then what I'm going to do, and this is why I showed you what a frequency polygon is, then what I'm going to do is I'm going to create a frequency polygon out of this. And I'm going to connect these points, and we're going to see something that looks like this. Okay? Now, the narrower these bars are, the more this is going to look like a smooth curve. And this looks like something I know that you probably covered in high school at some point. And what do we call this kind of a curve? What do we call this curve? Yeah, it's the normal curve or the bell curve, okay? And it really isn't a curve, it's a polygon. The reason it looks like a curve and we talk about the normal curve is because when we talk about this stuff, this x-axis is tremendously long, wide, okay, in terms of our interval. And so, these are really narrow, and when we connect all these little narrow columns, it looks like a smooth curve. And if you've taken calculus or other math stuff, you know that you can get a curve when this approaches infinity and blah, 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 blah. We're not going to get into that. This is not a math course, okay? But I hope that you can see now that a normal curve represents the outline here of this frequency histogram. And that there are things underneath it. And that's a very important concept that we're going to take advantage of later when we're making our decisions and doing more descriptive stuff. I'm going to clean this up a little bit, okay? But I'm going to replicate this in a smaller fashion. Like, that's the dirty little secret, right? So here is our normal curve, okay? That's typically how you see it, and that's why I say there's an implied y-axis here of frequency, and of course, underneath this curve are all the blocks, okay? Are all the blocks. And I don't want you to forget that, okay? I don't want you to forget that. That is, when you see a normal curve, it's just as an outline of what these blocks look like, okay? It's not transparent. It is opaque, filled with blocks, all right? And these are x values here. That is, it is the number line, okay? So that's what a normal curve is. I haven't put any numbers in here because this is generic, okay? This is what a normal curve looks like. The reason that we talk about normal curves so much is because normal curves are really quite ubiquitous, okay? Normal curves are ubiquitous. Now, if we were in a classroom, I would really hope that someone would raise their hand and say, Dr. Speck, what does ubiquitous mean? You just said ubiquitous. What does that mean? Okay. Well, first of all, let's spell it. It's spelled just like it sounds. Ubiquitous. Ubiquitous. Okay. Ubiquitous. And if you have any plans on going to graduate school or anything like that, this is a very common vocabulary word in the GREs, and people who are in graduate school know what this means. So you're welcome, right? You're learning it now. Well, what the hell does it mean? Ubiquitous means that we see that it's all over the place. It's very common, okay? Normal curves are ubiquitous. If we measured the height of all female students at Utica College, and we plotted it in a histogram like this, what we would find is a normal curve. If we did it for male heights, what we would find is a normal curve. If I looked at average temperature for a particular date, what we would find is that there would be a normal distribution of temperatures, okay? If I went outside and I picked all the leaves off of a tree and weighed each of those leaves, I would find that there's a normal curve. If I went to Lake Ontario and put out a big net and caught fish all day and weighed a certain, I'm weighing all of the trout that I catch, lake trout, I would find that the weight of the trout would form a normal curve. Many times when I give exams, I see normal curves. If I did running speeds of beagles at the kennel club, I would find that their speed of running would create a normal curve. We see normal curves all over the place, okay? They are ubiquitous. And so we learn a lot of our statistics from normal curves. And so this is what a normal curve is. This is what it's, what it's comprised of. Values of whatever variable we're measuring, frequency, and what we find is that this pattern looks like a bell, right? A bell-shaped curve, a bell curve, a normal curve. And what I want to do now is talk about our statistics, our descriptive statistics, and how they map onto this normal curve, okay? And so let's take a look. Well, could we identify, even though there's no numbers here, because our descriptive statistics are conceptual, we can compute them if we had the actual numbers, but they're also conceptual. All right, this is another theme that I've talked about before. Could we identify where the mode is in this distribution? And the answer is, I hope you could, because what am I asking you? I'm asking you, what is the most frequent score? That's the mode, right? The most frequent score is the mode. Well, if the y-axis is frequency, then what we're going to do is we're going to find the highest spot. We're going to find the highest spot in this curve, which is right here, okay? That's the most frequent. And so that means that right here, that's the mode, okay? The mode is the most frequent score. I know that this is the highest point on the graph, the most frequent, okay? And so I know that this is the place where the mode is going to be, okay? Now, here's a question. I want you to think about it. I'm going to share another one of my frustrations. For this class, sometimes if you don't know the answer like that, that's okay. It doesn't mean that you can't figure it out, right? Because these things are figure-outable. I mean, if I ask you what the capital of Idaho is, that's a question. I mean, you either know it or you don't know it, right? Of course, all college students know their state capitals. So the capital of Idaho is, right, it's Boise, Idaho. And that's not something to figure out. It's a factoid, okay? And you can always just look it up. Just Google it. In this case, I'm saying, well, what is the median here? And really what I'm saying is, where is the median? Where would the median be? Well, can we figure this out? One of the things about a normal curve is that it is symmetrical. I mean, hypothetically, a perfect normal curve is symmetrical around the vertical axis. All right, what does that do for us? Well, that means that 50% of the boxes, 50% of the boxes, 50% of the boxes, I'm not talking about a score, I'm talking about the number of boxes, the proportion, the percentage. If this is symmetrical, then 50% must be here, and 50% must be here. So, can we figure out where the median is? Well, let's go back to our, see, this is, I always encourage people, this is a stepwise, something, a concept that you can figure out. If a normal curve is symmetrical, 50% here, 50% here of the boxes, then can that help us understand the median? And the answer is yes, because the median is the place in the distribution. It's the place in the distribution where 50% of the scores fall at or below. It's the place in the distribution where 50% of the scores fall at or below. And since we know this is symmetrical, 50% of the blocks here. I don't have any scores. I don't know what the X values are, but guess what I know? I know that the median is right there as well. Okay? So the mode is there because it's the most frequent. The median is there because 50% of the blocks fall at or below. Now, this is something else you must think about and maybe unlearn from high school. These two things are not synonyms. These two concepts are not synonyms. They are not the same thing. They end up falling at the same place on a normal curve. That's a coincidence. That's a coincidence, okay? The mode is the place where the most frequent score is. The median is the place where 50% of the scores fall at or below. In a normal curve, those two things are at the same place. But in our next video, I'll show you that that's not always the case. They're not always at the same spot at all. And they have very different meanings. Okay? So the mode, the median. What about the mean? What about the mean? Well, today's our lucky day because we're going to finally understand what the mean means conceptually. Okay? You guys have been calculating averages for years, right? Your average test scores, your average running speed, the average on your bowling league, or whatever it is. You can calculate it, but I'm not sure you know exactly what it is. I mean, if you say the mean is the average, all you're doing is giving it a different name. I could say the mean is purple. That doesn't help me understand it anymore, right? Well, as it turns out, and as some of you already know, the mean is also at the same spot in a normal curve. But we don't know the concept of the mean yet. Like I said, today's our lucky day because we're going to learn it. Well, the mean ends up being the fulcrum. This is another great word, vocabulary word. It's great for Scrabble, by the way. Anybody know what a fulcrum is? Anybody know what a fulcrum is? Well, do you know what a seesaw is? Or a teeter-totter in the playground? Guess what? That teeter-totter balances, right? And that balance point is called the fulcrum. The balance point is called the fulcrum, okay? And so what we're going to do here, remember these are all blocks underneath here. These are all blocks. These are blocks, okay? All sorts of blocks, 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 blocks. I mean, if we put all those blocks on a plank, right? If we made this three-dimensional and this was all actual wooden blocks, the place where it would balance is the mean. That's the fulcrum, okay? So the mean is a balance point. However, in this case, it's very confusing. And this is why I wish in high school they wouldn't focus so much on the normal curve. Because in order to learn the difference between these, we need to look at curves where they are different. With a normal curve, they're all the same. Plus, even if you now know that the mean is the balance point, the fulcrum, in this case, you may think that it balances the number of blocks on each side. And it does in this case. But that can be very confusing. Let's look at another distribution, and I'm going to bring this up a number of times because it's an illustration of the fact that the mean doesn't necessarily balance the number of blocks. I'm going to repeat that. It's very important. The mean does not necessarily balance the number of blocks. It does here. That's a coincidence. Let's look at another distribution, a simpler distribution, okay? Let's look at this distribution, okay? Our n here is equal to 4, right? What is the mean? What is the mean for this group of 4 scores? What is the mean? Everybody got it? 2 plus 2 plus 2 is 6, plus 10 is 16, divided by 4. So, right, we're going to do let's do our formula. 16 divided by 4. So the mean for this distribution is 4. It's right here. This is the balance point, okay? That is true. You can figure it out. Now, when we look at this distribution, I want you to notice something extremely important. When a professor says that, you need to put an asterisk in your notebook, right? I mean, this is something you need to pay attention to. The mean is the balance point. Is it balancing the number of blocks? The answer is no. It's absolutely not. There's 3 blocks on this side. There's 1 block on this side, okay? So it doesn't balance the number of blocks. But it is the fulcrum. It is the balance of something. Well, I'm here to tell you what it is, okay? It is the balance of the deviations from itself. You're like, what? What? How far away is 2 from 4? Well, minus 2, right? How far away is this 2 from 4? Minus 2. How far away is this 2 from 4? Minus 2. Minus 2, minus 2, minus 2, right? How far away is 10 from 4? Plus 6. If we add up these deviations, minus 2, minus 2, minus 2, that's minus 6, and plus 6, so we get 0. That is, it balances the deviations. So the fulcrum here is not the number of blocks, even though that's what happens here. It's just a coincidence. The balance is the deviations. The mean balances the deviations in a distribution. Suppose we made a mistake and we said, oh, the mean is 5. Well, if we had the mean at 5, then we would have plus 5 here, minus 3, minus 3, minus 3. And of course, that wouldn't balance, okay? There's only one place, this point right here, where the distribution balances, and that point is our mean. Now that concept is still pretty obscure, but we'll talk about that as the semester unfolds, okay? But these are our 3 what are called measures of central tendency. This is chapter 3. These are measures of central tendency: mean, median, and mode. These are 3 measures of central tendency. In the next video, I'll talk about those more. The mode is the most frequent score. The median is the place in the distribution where 50% of the scores fall at or below. The mean is the fulcrum. It's the balance point, but it balances the deviations. It doesn't necessarily balance the blocks. It does in this case. That's a coincidence, okay? So in the next video, we'll talk more about the mean, the median, and the mode, and we'll talk about distributions that aren't normal, that aren't a normal curve. I mean, this is not a normal curve, okay? And we'll figure out where the mean, median, and the mode is here, and we'll do some other graphs of distributions that are not normal but are common. This is the most ubiquitous, the normal curve. Okay, I'll see you. If you have any questions, make sure you email me, okay?